The history of the colonization of Mercury can be split into two different time periods. The first period involves the early frontiers of humanity conquering our solar system. In this period, Mercury would not be as extensively used as other planets due to its extreme weather conditions. The second period involves the late stages of human development in the solar system. Because of the advantageous position of Mercury right next to the Sun, humanity will use it extensively for one big purpose: the construction of a Dyson Sphere. This would be the last step in humanity's history before conquering new star systems. In the first period of the colonization of Mercury, the planet would mainly be used to study the Sun due to its close proximity, as well as Mercury itself. Scientists could get an unprecedented view of solar activities like sunspots and flares, helping us understand the Sun's behavior and its impact on space weather. At the same time, being on Mercury's surface would allow for in-depth exploration of the planet's mysterious landscape, such as its craters and unusual geology. This dual focus, studying both the Sun and Mercury, could provide valuable insights into planetary science and solar physics, benefiting our understanding of the solar system. Using solar panels on Mercury to generate electricity could be highly effective yet challenging. Mercury, being the closest planet to the Sun, receives significantly more sunlight than Earth, making it an ideal location for solar energy capture. The long Mercurian day, lasting about 59 Earth days, would allow solar panels to continuously absorb sunlight for extended periods, potentially generating vast amounts of electricity. However, this comes with the challenge of extreme heat, as temperatures on Mercury can soar to levels that could damage standard solar panels. Therefore, the solar panels used on Mercury would need to be specially designed to withstand these harsh conditions. If successfully implemented, solar energy could be a powerful and consistent source of electricity useful for any activities on the planet. Other than that, human activity on the planet would be minimal until the later stages of the development of our solar system. Mercury is, again, a planet of extremes. It's incredibly close to the Sun, leading to surface temperatures that can reach a scorching 800 degrees Fahrenheit. However, this is primarily true for the equatorial regions. The poles of Mercury, in contrast, are a different story. The idea of starting the construction of a Dyson Sphere from the poles of Mercury might sound like pure science fiction, but it offers some intriguing possibilities. Just so everyone is on the same page, a Dyson Sphere is a hypothetical megastructure that encircles a star, capturing a significant percentage of its energy output. Why choose Mercury's poles? Mercury is the closest planet to the Sun, making it a logical starting point for a project aimed at harnessing solar energy. Being close reduces the distance materials need to be transported to begin construction. Mercury is rich in metals and minerals. These materials could be essential in starting the construction of a Dyson Sphere, especially since transporting materials from Earth or other planets would be impractically expensive and challenging. The poles of Mercury, unlike its equator, have more stable and cooler temperatures. This makes them more suitable for establishing construction bases and machinery which might not withstand the extreme heat of Mercury's equatorial regions. Also surprisingly, Mercury's poles are home to significant amounts of ice, hidden within permanently shadowed craters. This ice could be a vital resource, providing water for colonists, essential for sustaining life and potentially for fuel production. While constructing a Dyson Sphere, energy is a crucial requirement. The consistent, albeit less intense, sunlight at Mercury's poles could be harnessed to power the initial stages of construction. Due to these conditions, humanity would build two big colonies on the planet, one on the south and one on the North Pole. These would later be connected by railway or similar transport systems. The primary function of these colonies would be to support the manufacturing and assembly of components for the Dyson Sphere. This would necessitate large industrial complexes, possibly using automated systems and robotics for the manufacturing processes. The colonies would need to support a human workforce, even if much of the labor is automated. This would require robust life support systems, including radiation shielding, temperature control, and facilities to recycle water and air. Living quarters would be designed to ensure the physical and psychological well-being of the inhabitants. Continuous innovation and problem-solving would be critical. The colonies would likely have dedicated areas for R&D to improve construction techniques for the Dyson Sphere and to solve the unique challenges of living and working on Mercury. Given Mercury's harsh surface conditions with extreme temperature fluctuations and solar radiation, a subsurface transportation system might be the most viable option. Tunnels or tubes could be constructed beneath the surface, providing a shielded and temperature-controlled environment for transportation between the two colonies. This could be achieved through advanced drilling and tunneling technologies. If the technology allows for constructing stable infrastructure on Mercury's surface, maglev, magnetic levitation, or other forms of high-speed trains could be an option. These would need to be highly adapted to Mercury's extreme conditions. Efficient systems for the transportation of materials and personnel between the colonies and to orbit for Dyson Sphere construction would be essential. This might include space elevators, magnetic launch systems, or other advanced space launch technologies. High-capacity communication systems for intra-colony and interplanetary communication would be necessary for coordination of the Dyson Sphere project and for maintaining contact with Earth and other human outposts. In summary, these Mercury colonies would be highly specialized, focusing on industrial production, space logistics, and supporting a workforce in an extreme environment. The scale and complexity of building a Dyson Sphere would drive the design of every aspect of these colonies, making them unique in human experience and engineering. In the envisioned future colonization of Mercury, the planet serves two distinct roles. Initially, Mercury is a scientific outpost primarily utilized for studying the Sun and Mercury itself due to its proximity to the Sun. This phase involves deploying advanced solar panels to harness the intense solar energy despite challenges posed by Mercury's extreme temperatures. Mercury's unique position and long days make it an ideal location for in-depth solar studies and understanding its own geology and landscape characterized by extreme temperature variations. In the later stage, Mercury becomes pivotal in the ambitious project of constructing a Dyson Sphere, a megastructure designed to encircle and harness energy from the Sun. For this, humanity establishes major colonies at Mercury's poles, chosen for their relatively stable temperatures and resources like ice. These colonies are interconnected and equipped with advanced industrial, life support, and research facilities focusing on the manufacturing of Dyson Sphere components. They represent a significant leap in space engineering and logistics, tailored to support a workforce in Mercury's extreme environment and are essential in the transition of human endeavors from solar system exploration to interstellar conquest. If you are seeing this, thanks for watching until the end. The next episode in my series about humanity's colonization of our solar system, we will be focusing on Venus. If you don't want to miss the next episode, please consider to like and subscribe as this helps me out a lot. See you next time.